Where does it go?
It goes to your GT account,
Cool.
like media space. So it stays there for like 2 weeks. So that's convenience.
So I can get that off and then
Yeah.
put on
It also
YouTube or
doesn't
something.
right on your-
Oh, that's huge. Okay, well it says it's recording. Yeah. Oh, we got more people. Welcome.
Basically, like how they're good.
All right, I think we'll start. May I have everyone's attention? No, you're good. But thank you for coming to my small talk on service codes. Basically, this is a type of quantum error correction for quantum computing. And can I just get a show of hands? Who has had experience with quantum computing before? So we got a couple people. All right. I guess a little bit more specific, quantum error correction. Yeah, okay. So that's kind of where it drops off a little bit. So I will motivate what quantum computing is and also quantum error correction. Okay. All right. Now, first we get into the juicy stuff. What the heck is a qubit? A qubit, for the purposes of this talk, is just a 2D complex vector with magnitude 1. And honestly, you don't even need to think about that very much. All you need to know is what these little weird things are. The math notation of them. So we have the 0 qubit, which is just the 1, 0 vector. The 1 qubit, which is just the 0, 1 vector. And there's these two, which we don't really care about that much right now, but they're just a linear combination of those other two vectors. And you might be asking, well, what's a qubit physically? It's whatever this little dot is. It's like a little singular atom right there. You can actually see it. Take a picture of this, which I thought was pretty cool. But an atom can represent a state like that using, lasers or something. That's more on the quantum physics side. So we're not going to care about it that much. But all you really need to know is a qubit is represented by this vector. Yeah.
Is it always like the first quadrant?
No, so it can actually be in any quadrant. So yeah, that sphere picture, that's a good point. This sphere picture is kind of showing like the rotation of the qubit. So you have a bunch of angles that you can represent the qubit with, and that's represented by whatever the numbers in the vector are. So it can literally be any point on the sphere, as long as it's exactly magnitude 1, which means it's perfectly on the sphere. And also, this is supposed to be like an interactive lecture. So if you have any questions, please feel free to stop me and just ask a question. This is more towards, I'm trying to get everyone to like understand what I'm talking about rather than just like show off how complicated this is. Because it's not complicated once you understand the basics. So yeah. All right. Now, why do we need quantum error correction? And what is that anyways? Well, when we do quantum computation, you might have heard of it's like super fast compared to classical algorithms. That's true for certain algorithms. One example is factoring numbers. If you can efficiently factor numbers, you can break the entire internet. And this is because, well, take Bitcoin, for example. They are secured. Bitcoins are secured through factorization. And it's secure because it's hard to do. So if you try to factor someone's private key, then you're gonna have a really hard time. It's gonna take millions and millions of years, billions even, to do that. That's why we can say it's secure. But if you have an efficient way to do that, then you can just steal whoever's Bitcoins and you can say, well, give them all to me and then sell them off for money and make millions of dollars. And obviously no one's done this yet because there isn't a good way to do this. But quantum computing provides a good way to do this through certain algorithms, one of which is called Shor's algorithm. So I'll show you a little quantum circuit really quick. You might be asking, what is this thing? This whole diagram I just showed? This is the quantum circuit representation of Shor's algorithm. And you don't need to understand what it does. Only kind of what each piece means. So each horizontal line represents a cubit, and it starts on this side. Starts initialized as 0. And then as it goes this way, it might run into some gates. So the square, each square is a gate. And that'll change the qubit a little bit, like a matrix, like multiplies the vector by a matrix. And so each qubit goes through time this way until we get to this signal, which means measure. And that takes the value of the qubit and turns it into either a 1 or 0. So it goes from any point on that sphere into just a 1 or a 0. So with Shor's algorithm, we start out with, our numbers that we want to factor. At the very end up with the factored version of the number. So it's not important how that works right now, but this is just kind of what a circuit is. In real life, though, yeah. Question?
The number you want to factor is like, instead of 1 or 0, it's a 1 or 0 qubits.
Yeah, so you can represent it in like a bunch of qubits. So if you take like 10, if you want to put that into binary, how would you do that?
I'm quizzing you right now.
Yeah, it's interactive. I don't know. I forget what 10 is, but you put that into binary. But then the quantum version of binary is you put these 0 and 1 qubits instead of just 0 or 1. So it's kind of like that. But honestly, the details of Shor's algorithm, that's not what we're going into today. Instead, we want to know what happens when you implement it in real life. And you'll notice, what are all these red squiggles? Why do we have these here? Well, you remember what that qubit looks like? It was literally a singular atom. If we shine a light on that atom, what's going to happen to it? Yeah, something bad's going to happen. Maybe it jumps up in energy level from chemistry, if you remember the like electron clouds or whatever. If you shake the table that it's on, maybe the atom jumps out of that little trap it's in. If you breathe on it, maybe it'll disappear. Bad things can happen very easily to these qubits. So that's what these red squiggles are, is small environmental actions that can cause an error in the qubit. And so if you remember that sphere that I was talking about earlier, that could mean any qubit. A qubit's like a point on that sphere. Shaking the table might make the qubit jump to some different point on the sphere. And obviously that's bad because we want to get the correct solution, not some random error-prone solution. So how do we fix this? How do we fix this issue? Through quantum error correction. So that's the study of figuring out how to correct these errors that happen with our qubits. So the basis for a lot of quantum error correction methods is, instead of taking one atom and using that atom for our computation, what if we take 100 atoms? And each of those 100 atoms, we use them and we combine them through some special way so that they represent one qubit with a lower error rate. So if there's a rate of maybe 5% for each atom individually, then the rate, maybe if you take the average of all those 100 atoms, maybe the rate goes down to like, what would it be? It's much smaller. It's much smaller. Because if an atom if you get one singular error out of those 100 atoms, right? If you take the average, that's not going to affect it very much. But maybe if you have like 70 errors, that's what, 5% to the 70th power. That's like, it's extremely small. So that's very rarely going to happen. But only then will you actually have like a real error. So this idea is taking a bunch of these physical qubits and combining them in a special way to make one logical qubit that has a much lower error rate. Does that make sense to everyone? Yeah.
We said taking independent events, and if you keep adding more and more, error rate goes down because like multiplying each one, so that chance.
Exactly. So yeah, exactly what you said. You have independent errors for each of your qubits, but it's really rare that a lot of those errors happen at the same time. Therefore, if you take like, the average, then the error rate goes way down. Yeah,
How does that affect the time?
the time. Yeah, so that's actually a good question because this is one of the fundamental problems of quantum error correction is like if you wait a really long time through your circuits, you might notice on my slide back there, some of these qubits don't have gates happening to them. Like here, see this qubit has a bunch of opportunities for errors to happen, even though there's no gates happening. So that's saying if you have a qubit that's idling or nothing's happening to it, errors can still happen. So the longer you wait, the more errors can happen.
This is that's so different there, that when nothing's happens and when it goes to a gate.
That depends on your architecture. Exactly. It's like if you're using photons versus electrons versus nucleus or like an atom, like it definitely it changes based on that. But when you apply a gate, sometimes the error rate goes up a little bit.
You got it.
Yeah, yeah.
Because we have multiple samples, so are you gonna run it multiple times, or you're gonna have different computers running, or different kinds of computers?
Yeah, so generally you'd run it multiple times, but each time you run it, you have a different set of errors that could happen. And so we want a way that when we run it, we want to figure out what those errors are and how to fix them. And we need to do this doing some kind of method. So the method that I'm going to present to you today is called surface codes. That's a pretty modern method. A lot of people are studying right now. It's one of the more promising ones. There are better methods, but this one works really well with current hardware that we have. So that's why there's been so much studying into it. Okay, now as a little sneak peek of what's going to happen, I drew a little diagram. It looks like this blue and red checkerboard. And so this is what a surface code is, and I'll explain throughout this presentation how we can build our way up to this. Okay, let's start out with one qubit in a circuit. So here, it's initialized to the 0 state. And then through this little line, we go through time, and then we eventually measure it with that meter within square. Okay. So this is with no errors. But as I mentioned before, and as your question, Ethan, was mentioning, if you wait with a qubit, there's some probability of error. So one example of this is called an X error, and that's represented with that little plus circle thingy. And so there's multiple types of errors. Another is called a Z error. It's represented with a little Z box. And then it's also possible that we have both kinds of errors or even something different. Because remember, when you shake that table with the like atom in there, it can go anywhere on the sphere, not just to like a singular point. So you might be asking, why am I condensing this into just these kinds of errors? Well, as it turns out, I don't know the exact math behind it, but probabilistically you can represent any type of error with like a linear combination of these. So through a bunch of different like trials of your computation, you can correct it pretty well. So we're only gonna be focusing on these. Yeah.
What are you trying to bet in? What exactly doing?
Yeah, so that's a good question. So remember the qubits, the 0 and the 1 qubits that I mentioned? There's no pens. Does anyone? Oh, perfect. So we have our 0 qubit, which is like a 1 0 vector, 1 qubit, which is our 0 1 vector. So an X error, for example, that's the one top right, will turn a 0 into a 1 qubit. And it'll turn a 1 into a 0. And that's bad, obviously, because we don't want these errors to happen. So we have to figure out how can we correct these errors. And then a Z error will turn, this is less important right now, but it'll turn a 0, do nothing to a 0, but then it'll turn a 1 to a -1. Yeah.
Why do we care about what type of error?
Because, let me just write this really quick. We care because we correct them differently. And they have different effects. So imagine we have a, this is an X error. So if we have an X error happen on our qubit, but we think that a Z error happened, well, we'd be here, right? And we say, well, if it's a 0, then our original thing without the error is still 0. But if it's a -1, then our original qubit without the error is just a 1. When in reality, if it's a 1, it's actually 0. And if it's a 0, it's actually a 1. So we treat these errors differently because they have different effects on our qubits, and we need to correct them correctly in order to do our computation without errors. So this will make more sense as soon as we kind of get into error propagation. So I'm going to present this quantum circuit with Q0. So can everyone see where Q0 is on that circuit? We call Q0 and Q2 data qubits. And then we call Q1 a check qubit. And then we have a little quantum circuit here where we have some C0 gates, which are the blue things, and then some other gray things, where this should look familiar. Does anyone remember what this one is?
This a meter.
Yeah, it's the meter. Yeah, exactly. So we'll call it a meter for now, but it's also called like a measurement. But we'll call it a meter for now. So I want to get into what's called error propagation. And we're only going to be looking at X errors for now. So remember, everything from now until further notice is going to be an X error. Okay. What happens if there is an X error on qubit 0? Well, we can see it propagates forward, and this will go on indefinitely. But also when a C0 gate happens, it goes through this C0 gate. It goes through from the smaller to the larger circle, and then it goes and gets caught by the meter. So this is important. This is important. Now, can I ask, what would happen if instead of this, there was an error on Q2? Someone tell me what would happen to the meter. Yeah. No error on qubit 0. Imagine there's only an error on qubit 2. Yes, exactly. So here's a little diagram. So if there's only an error on Q2, then it gets propagated up and to the meter again. Now, what happens if there's an error on both Q0 and Q2?
Both are gonna propagate.
Both are going to propagate, but then something special happens. Both propagate, but they cancel out. When two errors meet each other, they explode and cancel out.
Only two answers.
Yeah, exactly. So if two X errors meet each other, they'll explode, and then nothing will happen to the meter. As you can see, the meter isn't red.
So they like fix each other.
Yeah, they fixed each other. Exactly. So yeah, that's a good question. When I say propagate, I just mean like, how does the error go through the circuit through time? So like, as we go from the left side to the right side, where does the red go? Okay. Now, last, if there's an error on the check qubit in the middle. You can see it also turns on the meter. But this case, we'll come back to later. We don't really need to look at this right now. Okay. As a recap, so the meter or the measurement is on if there's exactly one error, and is off if there's exactly 0 or 2 errors. So this is kind of cool, right? Because if there's one error, we can detect if there's an error. We can now detect that. But we don't know how to correct it. The whole point of this is like, can we fix the error if it happens? Because they're gonna happen regardless. So when they do happen, can we figure out which error it is and how can we correct it? So can someone tell me how you would correct this kind of error if you figured it out? Yeah. Yeah. So if you knew which one it was.
I mean, if you know it's X,
Mhm.
then just make a 1 a 0 0.
Exactly. And if you know if it's a Z, then you just do this. But here's my question to you. How do you know which qubit the error's on? Yeah. Timing. So can you elaborate on that? Yeah, I mean, it will take longer for it to, there's definitely a timing difference. But the problem with that statement is we don't know. The only thing we know is if the meter is on or off. So it's not possible. Because remember, if there's an error on Q0, the meter's on. If there's an error on Q2, the meter's on. We can't distinguish between those two because we don't know what Q0 or Q2 is. So how do we correct this? Well, we have to add another one. We have to add another little qubit. And so here we got our first fault tolerant code. And that fault tolerant just means we can correct the error if one happens. So my question to you guys, what happens if there's an error on Q0? Is what?
No, it won't be on because that is two, right, multiple of two to be on, right? For the meter to be on, you need
Close.
0.
0 or
So I'm
two.
multiple of two, right?
so it's actually for it to be off, it has to be 0 or 2. For the meter to be on, it has to be exactly one error.
Okay.
But be careful, now we're connected to another thing. But you're right, it will be on because it's literally the exact same as last time. The error will propagate through the CNOT and then into the meter and turn it on. Now, next, what happens if there's an error in the middle on Q2? Second meter. And the first one, oh, sorry, let me rephrase. What if there's only an error in Q2?
Will just be on the
Just be on the second one? Okay, you're close, Yeah,
It wouldn't keep, because it would keep going.
exactly, yeah. Because the error, it keeps going throughout the data qubit. So you're exactly right. See, it'll propagate like that. It'll be on both. Now what happens if there is an error on Q4 only? No more errors, just Q4. Hmm? Exactly. Just the second meter will turn on. Okay, now we'll do some strange ones. What if I forget which one it is next. What if there's an error on Q0 and Q2?
Just this. Yeah, it's the first one came.
Mm-hmm. Oh yeah. Yeah, so the first one will cancel out, and then the second meter will be on because it doesn't cancel out. Can I ask why doesn't the second one cancel out?
Because there's only one.
Yeah. Yeah. If there was a second error, then it would cancel out. But there's only one error, so it doesn't cancel out.
So,
Yeah.
all three.
Yeah, that's one of the cases that's next. Not just next though. We'll get to that. Okay, what happens here?
First one.
First one turns on?
Second one.
Yes. Does everyone agree? So that's correct. First one is on, second one cancels out, so it's off. What happens if the two outer ones have errors? Both on. Correct. Now, this was the one that Ethan was talking about. What if all three are on? Both are off? Why?
For the first one, 0 and 2, they will cancel out.
Mm-hmm.
For the second one, 2 and 4.
Yes, perfect. Perfect. So both of them cancel out. Both meters are off now.
So that's like, because then you wouldn't know if all the 9 about like, we should see what's really rare.
Yeah. Yeah, exactly. It's really rare if those happen. So what we know now is we can say if both meters are off, then there's either 0 errors or there's 3 errors, right? If the first meter's on and the second meter's off, then either there's just an error on Q0 or there's an error on Q2 and Q4. And keep going on with the 0, 1 and then 1, 1 case. And exactly like you said, if there's 3 errors, well, remember the probability of an error we're saying is like maybe 5%. So if there's 3 independent errors, what's the probability of that happening?
Or D is
Just-
1.
Yeah, it's just 0.5 or it's 0.05 cubed, right? Because it's 0.05 times 0.05 times 0.05. They're all independent. And that's way smaller than 0.05. That's super rare. So 3 errors is way rarer than having 0 errors. Does everyone agree with that? Now, what about the second case? When there's 2 errors, what's the probability of that? 2 independent errors.
Two independent, so that's 1/400.
Put 0.
Yeah, so it's if 1 error is probability P, then 2 errors is probability P times P. So it's just 0.05 squared or 5% squared, right? And 5% squared, that's like 0.25% or something. Way less probable than 5%. So it's much more likely that we have either no errors or 1 error than if we have more than that. And so what we could say is, well, let me ask you, if we have if we measure our meters and we get the first meters on and the second meters off, what should we predict that the error is? The first meters on. What was that?
Q0.
Q0? Okay, yeah. And why would we not predict Q2, Q4? Yeah, exactly. So it could be Q2, Q4, but the chance of that happening instead of just Q0 is super low. So we just don't care about it. So here we have our first fault tolerant code. Whichever the meters measure out to be, we can figure out what the error was or errors were on the code. Actually, just one error, because if there's multiple errors, then we'll correct it incorrectly. We'll do the wrong correction. But yeah, now we can correct one error. And so I don't know, you might have been paying attention. There's some graphs next to all of these diagrams. Let me go back and show what they mean. Going all the way back. This is so laggy. Give it a second. Oh, a little bit. Oh yeah, that's why I confused in French. I'm trying to learn. Oh no, it started at the beginning. Okay. Let's go. Let's go. Okay, here's the graph. So this looks like just a line and a dot, but this is going to be a graph representing this entire circuit diagram. So each edge, the top edge, represents the first data qubit. The middle vertex represents, or the dot represents the middle check qubit, and then the bottom edge represents the bottom data qubit. Okay. So now when there's an error, we can see the top edge turns red when there's an error on the top data qubit. And then the meter, when the meter is red, then the dot becomes red. So the dot corresponds to the meter and the edge corresponds to the data qubit. So what happens? Let me ask, what happens if there's an error on the bottom, just on the bottom Q2? What happens to the meter?
Turn on.
It turns on. And then what will the graph look like?
The bottom edge.
Just the bottom edge? Yes, exactly. So the bottom edge will turn on because there's an arrow on the bottom. And then the dot, it turns red because the meter's red. Now, can someone explain this one? Why does that graph look like that?
You're canceling, so the views off.
So the meter's off, so the dot's off. Yeah. And then, yeah, not paying attention to that yet. Okay, here we have a slightly bigger graph because we have a bigger diagram. But can someone tell me what the edges represent in this one? And same with the dots.
Yeah, these are Q, Q2, Q4. Be the meters.
Yeah. I mean, the edges would be Q0, Q2, Q4.
Oh,
Yeah. And then the dots are the meters again. So what happens if we have an error on Q0?
And a dot on the top and the edge will turn on.
Yes. So just like before, the error propagates like that. As in that meter turns on. So the edge will be on and the meter, the dot, will also be red. Now, what if it's in the middle? What if there's a error on Q2? What will the graph look like? Only Q2, so just the middle edge, both meters, so both dots. Now for Q4. Then we can keep going. So if we have the top, so Q0 and Q2 errors.
Q0. So it will be top and middle line.
Yeah, top, middle, and then bottom dot. Sorry, that should be that one. Yeah. So the top, middle, and then the bottom dot because the bottom meter's on. So yeah, I just wrote this for every single case we had. I'm sure you get the idea now. There. So can someone tell me why are both the dots off in this one?
They cancel out the errors.
So the errors cancel out, so the meters are off, so the dots are off. Okay. Back to where we were. We have a bunch of these graphs, right? And this is a much smaller representation of that whole circuit diagram. So how can we correct the errors from the graph? What parts of the graph represents the errors? The edges, right? So given the red edges, my question for you is how can we get the red points?
Follows the same error on the opposite.
Yeah, so if you draw the diagram, then like you said, those edges will cause the meters to either turn on or off. And then you can get the dots from that. And so the problem that we want to solve is actually another problem. If we're given just the meters, or we're given just the dots that are either on or off, how can we get which edges are on?
We know that when a dot is on, one of the edges is on. And if we only have one dot, we don't know which edge. But if we have two, then we can know which edge it is.
Exactly. Yeah, exactly. So observation, very smart. Each red dot has exactly one, I say incident red edge. That means one edge that pokes out of it. So every red dot has exactly one red edge that pokes out of it. And has anyone here done anything with graphs before, like graph theory or combo? Okay, depth first search. Might have heard of that one. So this is a common graph theory problem called a matching. And what does that mean? Well, given the dots, you want to find the shortest path between them that you can connect them with red edges. And it's a little bit awkward here because, well, look at this one, right? It only has one one red dot. So how do we figure out what the shortest path is from that to another red dot? Well, the answer is it's either we find the shortest path between dots or between a dot and the border, right? So some of these paths, they don't have the shortest path. Like this one, if we have just a red dot here, what's the shortest path from this dot to either another red dot or the border? Someone tell me?
Another red dot at the top, and infinity.
Yeah, well, at infinity is just the border, right?
Oh, okay, that was.
So yeah, like you said, if we just go up to the border, that is only one edge versus if we go down to the border, that's two edges. And if you'll remember, this is two errors. So if we just go up and we predict that it's the shortest path, then we're predicting that there's one error.
Remember, it's like finding the shorter path from a red dot to another red dot and or to an
Mhm.
to an edge.
So for each red dot, what's the shortest path from that dot to either the edge or another red dot? And so you'll notice if we do this algorithm, the ones on the left are all the shortest paths. If we split this in half, right? This dot, what's the shortest path right here? Just going down, right? Because if we go up, that's two edges, but if we go down, that's just one edge. For this one, we already did that. How about this one? Mhm. So right now, it goes to the border, that's two edges, but if we just put one in the middle, that's just one. How about this one?
There's no red dot or.
No, there's none, yeah. There's no red dots, so we don't need to do it. And so this way, given the red dots, we can predict where the red edges will be. Can someone tell me what that means in terms of errors and meters?
Do you know which?
Yeah, so given the meters, you can tell where the errors are, which qubits failed. And we say most likely because remember here, back,
It could be all three.
yeah. It could be either, for example, it could be either no errors or all three. But since all three is super rare, we don't care about the case. So if the meters are both 0, 0, then we predict that there's no errors. So just a little parallel there. Now, here's a curveball. What happens if we make a bigger graph and we get some bigger circuit, right? So we have 4 data qubits now, Q0 through Q3, and we have 1 check qubit, Q4. Now, I'm gonna ask, what happens if there's an error on Q0?
Then
Turns on, meter turns on. Like that. And then also look at the graph, right? There's an error on Q0, the edge turns on, and because the meter's on, the dot is red. What about if there's one on Q0 and Q1? Gonna be off.
Oh, that does.
And then what does the graph look like? You said the dot's off. What is the
You
whole?
said it just showing,
Mm-hmm.
and those two edges not totally red and not plus.
Yes, exactly. So yeah, we look like this now. And you'll notice it's the same exact pattern. Basically, if another error happens, then the meter will turn on. So if there's an even number of errors, the meter's off. If there's an odd number of errors, the meter's on. Like that. See how it cancels out, and then there's another error. So now we know each vertex is, or each meter is on for an odd number of errors and off for an even number of errors. So here I'm called the vertex of stabilizer. That's just the formal name for the meter. We call that check qubit stabilizer. So yeah, does it look a little bit familiar now? Got a bunch of those graphs in the row. So now starting to make sense. There's still some stuff we have to go into. But You'll notice the check qubits or the meters, those are the black vertices. The data qubits are just those edges in the middle. Right? So, okay, yeah. We have to slow down for a sec. Remember when I said everything we were doing is X errors? But what about Z errors? We're not caring about those up until now. So it turns out you can actually do pretty much almost the same thing with slight changes, and you can still detect Z errors. So to demonstrate this, the Z error is blue instead of red. What happens now? How will this error propagate? What's that?
It's not in one.
Yes, that equal is 0, right?
Mm-hmm.
It'll just be 0. So
Yeah, this is kind of a trick question. It actually doesn't do anything with the C0 because the way that these propagate, it's a little bit of linear algebra, but they don't propagate through the C0 the same. It's actually the opposite. So here, these are the things that need to be changed for our circuit to actually work. Currently, yeah, that little circle on the left, it starts in a Z basis, but it should start in an X basis. You don't need to know what that means for the purposes of this talk. The middle, the C naughts, they should also be flipped because as you saw, the Z error didn't propagate through it correctly, just did nothing. Then also that measure thing, we should measure in the X basis instead of the Z basis in order to actually detect those Z errors. You don't need to know what that means, but you do need to see what the next circuit looks like. So as you can see, it's slightly different. All we changed was that beginning thing. We changed this from just the 0. So this is basically functionally the same. We flipped all of these, and then we changed this from that meter. But the meter is still the important part. So now what happens if we try to propagate an error here? Same exact thing. There's a Z error on Q0, propagates down into the meter, and then the meter turns on. And also take a look at the graph, right? If there's a blue error, if there's a Z error, then it's blue. So the edge turns blue, but then the meter still turns on. And notice the meter isn't blue or anything, it's still red because the meters are either on or off. There's no like quantum special third state or anything. It's just either on or off. So that's why it's red. So what happens if there's a Z error on Q0 and Q1? What happens to the meter? Mm-hmm. Same exact thing as before, right? Yeah, I didn't have that, but here we have the Z stabilizer, which checks for X errors. Yeah, if this wasn't confusing enough, right? The creator of this have these two circuits, the one that checks for X errors and the one that checks for Z errors. We call them the opposite things. So the one that checks for X errors, we call it a Z stabilizer. One that checks for Z errors, we call it an X stabilizer. It should be the opposite, but it's not. Yeah.
how do you know like which one to check for, or do you just do if you?
That's a good question. Yeah. So how do you know which one to check for? Well, if you think about it, both types of errors could happen anywhere, right? So if an X error happens on the stabilizer that checks for Z errors, you're not going to detect it. So how do you know where you should put these stabilizers? The trick is you basically put them everywhere. You checkerboard them so that every qubit is connected to X and Z stabilizers. So it can detect both. So now that's what the colors mean is if it's has a blue background, that means that stabilizer is checking for X errors. And if it's a red background, that means it's checking for Z errors. Then conversely, blue means a Z stabilizer, red means X stabilizer. But I prefer to say that it checks for X errors and it checks for Z errors because it's easier to understand that way. Okay, now with the actual surface code, what happens if there's an error on this data qubit? No. So these edges turn on. Which which dots will turn on?
Or,
Four around. Close, close.
Wait, which area? That's the action.
Yeah, the X error is red.
yes.
So think about which stabilizer. Let me ask you this. It's an X error, so which stabilizer
Just
detects that X error?
Only the Z state.
Yeah.
Yes.
So the blue ones are gonna detect the X error.
The other-
Therefore.
It's like zero, which is stage.
Exactly. Yeah, exactly. If you're looking at that, that's how it works. So in that case, if only the blue stabilizers can detect this error, which dots will turn on? Yeah. Just those ones turn on. So we can detect that error that way. Now, if it was a Z error, right, those blue ones wouldn't be able to detect it because they only detect X errors. So then the red ones would turn on. Now, here's a slightly harder question. We got 4 dots now. Which errors or which edges would make these dots? Middle.
Lines,
So which one should I look at?
like one of the ones that's in the middle of blue box.
This one?
Yeah, like when I go to the next blue box, diagonal,
This one? Okay.
or like, yeah.
Okay, then what color?
Wait, so those are
Every, it would be all.
These are the meters.
Yeah, so those are diameters, so they're on, so we have to find out which edges are errors.
Which edges are? So these two, you said there's gonna be an edge between here, it's gonna be on.
So for, in the middle.
Now what color is it gonna be? Is it gonna be, if these blue ones detect X errors. So if these detect an X error, and there's an error right here, which type is that?
This is red.
Right. Okay. It's gonna be an X error. So if they detect an X error, then we think there's an X error there. Now, what about these ones? Let's do red.
It's here.
Z in the middle. Why is it a Z error? Because these ones both detect Z errors. That's covered, but yeah, these check for Z errors. And the shortest path between them is right there. So that's gonna be a Z error. So it's gonna be a blue one. Like that. That makes sense? Okay, so as a quick recap, Z stabilizers check for X errors, X stabilizers check for Z errors. Whoever named it that way, smart guy. And then, yeah, so we can make a graph of all these stabilizers. And given the red vertices, we can predict which errors most likely are going to happen or which edges most likely happen. So the algorithm we use for that is called minimum weight perfect matching. That's just the thing we were manually doing, trying to figure out which color the edges were. That's what the algorithm does. Okay, there's one small difficulty in our plan. What about this thing, right? If this meter on, it says that there's an error says that, there's an error here, but there's no error. There's just an error in the check qubit, no error in the data qubits. So this is gonna screw up everything we're thinking about, because like, if we think that one of the data qubits has an error, but they don't, and we try to fix it, then we're just creating an error. So that's not good. Consider this though. It's the same circuit, but we just copy and paste it a bunch sequentially, right? Now, what happens if there's an error in Q0? This is just from the basic case, but extended.
All the meters.
All the meters. That's right. Why is it all the meters? Keeps going. So we start out there, then all the meters. Now what happens? Yeah. It's just time. It's like each gate happens one after another, right? Now what happens if there's an error in one of the check qubits? Why does it stop after the first meter?
qubit that like recess it.
Exactly, it gets reset. So if it's reset, how can the error persist if you literally set the qubit?
Oh, wait, what's the meter?
Hmm?
Is the meter on the first one?
Oh, the first one, that's just me saying and there's an error there. That's not, this first gray one, that's not a meter. This is saying that you're resetting the qubit. This one's a meter, this is not. So this is just
Like,
saying,
so you're like the red and you're circling around red, so that means that there's an error, that's not.
yeah, there's an error. Maybe I should draw it a little bit differently to be more consistent. But yeah, this software is not very fast. Yeah. Okay, maybe not. Oh, I just shot myself in the foot. It's gonna take a minute now. Ah. No, it's fine. It's the computer. But can someone come up and draw? Actually, can someone explain why does it not go past that meter in that last case we were doing? Mhm.
So once it gets or detects that there's an error, it goes down to or whatever the last one was.
Yes, exactly. So this is some quantum physics right here, but whenever you have the meter in a circuit, it actually destroys the qubit. Mhm. Whenever you measure it, it destroys the qubit, and then you reset it, and then it becomes a qubit again. So that's some quantum physics. I don't actually fully know. I've never taken quantum physics, so I don't know how well it works. Nice weather today, huh?
It's like it's like you can only know so much about it, right?
Mhm.
It's like a position, you like don't know velocity.
Yeah, that is very closely related, yeah. Because it's like your quantum state is it has infinite accuracy in your quantum state. But then when you measure it, it's either one state or another state. It's either 1 or 0, right?
You're really, if you like want to measure, you have to shine a light, right?
Yeah.
The light hits it.
And that affects it. And then we only know like based on how many photons bounce off of it or something, if it's in the 1 or the 0 state. So here, yeah, imagine it might be a little bit more coherent if instead of circling this 0, imagine I put a little dot right after the 0. And then it's just another error. So, but you'll notice with this last one, if there's an error on the data qubit, all of the meters will flip. But if there's an error on just just the check qubit, only one meter will flip.
You're saying we do this like that same thing over and 3 times.
Mhm.
And maybe you look at the game to see how many were on, and that was on that first one was a better.
Exactly. So if you see that there's only one on, then that means that there is an error in the check qubit. But if all of them are on, that means there's a data error. So if we keep repeating the stabilizer for many rounds, we can detect errors on the check qubits and differentiate them with errors on the data qubits. So what does that look like for a surface code? If you just keep repeating the surface code over and over, it gets kind of crazy. So that graph is going to have a lot more vertices, a lot more edges. And this is why we have computers to do it for us, thankfully. So
You're just gonna like you have a surface, and you keep like adding layers or something.
Mhm. So it's like that surface code, but then we just copy it and paste on top and on top of itself a bunch of times.
Time.
Mhm.
You go above, you do like.
Yeah, time is that third axis. Okay, so that's actually what a surface code is. Now, you might be wondering like how well does this correct errors? And so we have a little graph here. The way you should interpret this is the bottom is the physical error rate, So that's like the 5% I was talking about. And we want the physical error rate to be low. Ideally, scientists will figure that out. The thing that we control with our error correction codes, though, is the y-axis, the logical error rate. And it's better if the logical error rate's lower. So as surface code goes down, logical error rate also goes down. So you want it to go down towards the bottom left. And you can see as you increase the size of the surface code. So the one on the very left is a d=3 code. D just kind of says like the size of the code. So that requires 17 qubits. This d=5 requires 49 qubits, and it gets much larger pretty quickly. But the larger surface codes, they do a better job at correcting errors. Therefore, the error rate is lower. Does that make sense?
So what is that for? Like the 7 one? So that-
7?
So that D7 growing
Yeah.
faster than the red.
It's because, well, we actually want to look at it going this way. So first of all, cut this part off. It's this in a second. But as the physical error rate decreases, logical error rate decreases even faster than these. So that means the higher I guess the bigger our surface code is, the better it will correct errors. As each qubit error, each physical qubit error goes down. Yeah.
Is D5 like a 2 to the 49? Big, like how big of a number? Can you
A
remember
number?
D5 or
Like how many qubits are in it, or?
yeah.
I think it's 2 or D-1.
It's so close. It's 2 times d² minus 1.
Okay.
That's how you calculate how many qubits are in it. So if you have
And it is how many qubits? Oh, wait.
yeah. So you remember those circuit diagrams from before? You had like 4 data qubits, 1 measure qubit, and you calculate it based on counting those. So you can look at this. Each of these are data qubits. This is a measure qubit. You just count all of them for code. It turns out to be 2d² minus 1. So what you should take yeah. Mhm.
Or is this square rate like 8.10 to the -3 like the threshold of for code maybe?
Yes, that's actually a really good question. The threshold. So why for some parts in this graph is the logical error rate higher than the physical error rate? Doesn't that mean that using this surface code is actually worse than just using a normal qubit? And the answer is yes. If your qubits are like really awful, like say the error rate on your qubit is like 10%, then if you combine all those qubits into a surface code, the logical error rate of that code is going to be even higher than 10%. But as you can see, there's this little intersection point where all these lines intersect. And that's saying above this, your surface code is going to be worse than a single qubit. Below this, your surface code is going to be better than a single qubit.
But wait, at 10 to -2, that's a physical error, but on the logical error is 2 times 10 to -2. So is it like that worse than the physical?
Oh, sorry. Let me explain it slightly differently. Here's your threshold. Above the threshold, it's garbage. We don't care about above the threshold. Below the threshold, the logical error rate decreases exponentially. So there is some point, right? This is 10. This is slightly, but the logical error rate is slightly higher than the physical error rate here. But as we increase, or as we linearly decrease the physical error rate, the logical error rate will exponentially increase. So that means if you just pass this threshold, if you decrease the physical error rate by just a little bit, then notice this is a logarithmic graph. The logical error rate will decrease exponentially, which is great because it's hard to get really accurate physical qubits scientists have been slowly, like very slowly, decreasing the physical error rate. But all we need is just a small decrease in it in order for the surface code to be exponentially better. So that's one of the reasons why it's so good. It's because it gets exponentially better as scientists increase the physical error rate just by a little bit. And another reason why they're good is, yeah, so exponentially suppress errors. Another reason why they're good is you might have heard of Google's Willow chip. Recently they made a D equals 5 surface code and proof of concept. It actually works. So their architectures work very well with surface codes just because of the way it's kind of constructed. Same with IBM. I think other architectures as well. But yeah, was that your only question, or did you say you had others?
Yeah, maybe was. Have been different shapes of that same type. Where
Mhm.
you have like basically a square with like the edges and 4 points.
Yeah.
Where it's like four, one check qubit per like actual data qubit. Surface codes sounds like it's a whole class of codes. Are there different like local topologies as well as just like different shapes?
Yes. So I was presenting a pretty simplified version of the surface code today. And this is actually what a lot of people have been using so far, but they started out as what's called a toric code. So imagine a donut and you put that checkerboard onto the donut. And so it's like a donut shape and you still have that checkerboard along the donut. So that's also a valid code. And then they figured out you can just put it on a sphere, or you can put it on a flat thing, or you can make even different shapes with it. So maybe you'd have like a rectangular surface code that's really long, or maybe it's like an L or something. And then, this is much more advanced than what's in the scope of this talk today, but you can even deform surface codes by like taking out some of the checkerboards in the middle, and that'll make new logical qubits. So you can have more than one logical qubit per surface code. It's super cool. And you can also, I didn't talk about how you'd actually do quantum computation on this. Like, how would you do an AND gate or an OR gate or CNOT gate, whatever the quantum gates are? There's ways you can do that within one surface code as well by turning off and on those stabilizers. Yeah. So you can do all the computation you need just on a surface code. Yeah. Yes. Yes. So superconducting, for those who don't know, is basically, there's a lot of different types of quantum computers. Some use, like I said, literal atoms, and they like shine lasers at them. And sometimes they use photons, or sometimes they use like diamonds, like nitrogen vacancies, like singular atom defects in diamonds. Then this other type is called superconducting, which it looks most similar to a normal circuit board on like a piece of silicon, which instead of using transistors, they use this thing called a Josephson junction. The point is, surface codes, because they only connect qubits nearby, you can represent the graph without crossing any of the edges. Because if you had to cross the edges, that means you have to put two wires that go through each other, but don't connect. That's hard to do on like a flat plane. So this works very well for superconducting, like IBM's heavy hex and Google's Willow architecture, just because of the way that it's planar. Yeah.
Would be something like, you mentioned that like for superconducting, you really don't want crossing lines.
Yeah.
However, like for surface codes, like the toric code, you said it was on a torus,
Mhm.
but you can't project that very easily onto like a 2D plane without intersecting
Right.
circuit connections. Are these like more complex surfaces of any use to QVC on superconducting?
So
Or like
that's a good question. That's a good question. So if you do have an architecture that can cross those lines, like atom array architectures, you can still perform like with those topologies, like the donut or the sphere one. But because it turns out you can actually turn it into just a square. Like the square is also valid architecture. That's why it works so well with superconducting. But yeah, all these other topologies, they allow you to put it on like different surfaces and have different connectivities, some local, some non-local. And for like theoretically, there are other codes that are similar to surface codes, but instead of having just like the nearest neighbor connections, like instead of it just being a checkerboard, maybe some of those dots in the middle would connect like across the code. And that might prevent, or that might provide some even better error correction than the surface code can provide. But that's basically impossible to create on a chip because you'd have to create those connections that go through other connections. So it's still useful to know about this stuff. Just when you're engineering it, these are the limitations to consider. Yeah. So yeah, that's the whole presentation. Thank you. And yeah, if you're wondering, that thing is what the actual diagram of a quantum circuit for a surface code looks like. That's why we use computers. It's kind of crazy looking. But yeah, if anyone has any more questions, I'll be happy to take them. Nope. All right, thank you guys so much for coming.
Thank you, Eli.
Thank you.
You going to quantum computing now?
Yeah, exactly. You'll be a master now.
Since the first meeting.
I've been good. Lots of work going on, lots of research.